I forgot. I promised you last Friday that there would be a little power video to watch. And then I didn't get it done Friday before I left school because, you know, who wants to do anything on Friday afternoon? But it is up there now. So thank you to folks that reminded me yesterday. If you haven't watched it, not a huge deal, but make sure you do watch it sometime in the next couple of days so that you know how to do the problems and also so that you're familiar with that. If you have questions about that, really, or anything else, remember by the end of this week, especially, you know, like Wednesday and Thursday are going to be really great days to review, to go over homework if you have them. So just let me know, okay? I'm very, very happy to help you out. We are going to put the Hooke's Law Lab stuff down on paper now that you've seen it, now that you've collected some data and you know kind of what's happening. So just to recount and to make sure that you have it in your notes as well, we're just going to, so this is the Hooke's Law Lab. And in the Hooke's Law Lab, what was it that you graphed? Mass and displacement, right? You graphed mass and displacement. And which way did you graph it? What did you put on what axes? Mass down here and displacement on the x, or on the y axis, excuse me. That sounded really goofy. And the displacement was measured in centimeters, and the mass was measured in grams. Okay. And what kind of a graph did you get? It was linear, wasn't it? For sure it was. And could you calculate the slope of that line? Yeah, and maybe you did, maybe you didn't, whatever, but you could, right? If you did, awesome. If you didn't, it's not a huge deal today. What I want to do is to take this idea and take it one step further. So before we do that, let's draw ourselves a little spring. So you might want to just remind yourself of what this whole thing looked like. So there's my spring, and I'm just going to put a little mass like that on the spring. And then I'm going to ask a really quick question because we haven't done one for a while. Could you draw a free body diagram of this mass? It means all the forces that are acting on that mass. Because we haven't done one for a little while. What's one of the forces that's acting on that mass? Gravity, but we're not going to just label it gravity. What are we going to label it? Indeed we are. The force of the earth. And which way does that one go? I should have asked before I drew the arrow. It goes down, right? The force of the earth on the mass. That's Fg. Any other forces acting on the mass? We're saying? The force of tension. So yeah, so I'm not going to call it tension quite, but it's essentially like a tension force, but I'm just going to call it the spring. Is that okay? That the spring is actually applying a force? Which way is the spring applying a force? Upwards. Absolutely it is. Force of the spring on the mass. Okay? And if you want to call that a tension force, you absolutely can. I'm just going to call it F sub S, or you could call it F sub E for elastic if you want to. Okay, I'm going to go ahead and just leave F sub S. Quick question for you. How do these two forces compare in magnitude? That's a good question, Ms. Carmel. If I set this so that it's not wiggling, we can call that what? It starts with an E? What's that? Equilibrium, right? Yeah? We haven't used the word equilibrium a lot, if at all. What does equilibrium mean? Do you know? Oh, you're the one that said it. What does equilibrium mean? It's like, that's a good question. It's a fancy word, though.
I mean,
go with your gut.
When everything is equal.
Yeah, that's exactly what it is, right? So at this point, we're throwing in some new words here. The mass is at equilibrium. Equilibrium. Equilibrium is just a situation when the net force is equal to 0. Yeah. Okay. If the net force is equal to 0, how do those two forces compare, friends? Equal in magnitude, right? Okay. How do you find the force of gravity? Say it loud. Mass times G, mg, right? So does it make sense to you if we write out a little F net equation, because, we can and it's been a while, and it's always good to practice these things. F net in the y direction is going to be equal to the force of the spring plus the force of gravity. That one's going in the negative direction. They have to add up to 0. So we can say that the force of the spring is equal to m times g. I skipped 2 steps there. I'm hoping that's okay. Move that up so you can see it a little bit better. Okay. And does it seem reasonable then that as the mass goes up, the force of the spring goes up, right? It's linear, it just does its thing, okay? So what I want to do is kind of re-sketch this graph, but instead of using mass, I want to use the force of the spring, because I really want to know how the force of the spring is affected. Is that okay? Now, we did the mass, we changed the mass, and it pulled on the spring. Right, so this was kind of the cause and the effect. If I'm talking about the force of the spring, we could also say that as I stretch that, it's going to change the force of the spring. Does that make sense? Because if I stretch the spring just a little tiny bit, does it make sense that the force of the spring is going to be there? But if I stretch it a little bit more, that the force of the spring is going to be a little bit bigger, right? The bigger my displacement, the bigger my force. And really what I'm trying to get to, I'm going to draw a new graph over here. I'm going to put the displacement on the x-axis. Trust me, this is one of those, okay, Miss Carbling, sounds okay, I hope, sort of things, okay? And I'm going to put my spring force on the y-axis. And then just real quick at your tables, sketch out that graph. What's it going to look like? Is it going to be curvy and funky? Is it going to be horizontal? Is it going to go negative? What's it going to do? Talk to each other real quick. It should not be too scary, my friends. And also that makes sense because you just How are we doing? Hey, Sid, did you guys draw a graph back there? We were discussing, what kind of graph do you think you want to draw? Linear goes up, right? Yeah. Something like this. And if we had a perfect system, where do you think that this should intersect the y-axis? At 0, 0. So because we're talking theoretical, I'm going to go ahead and make that happen, right? If we're actually having data in there, then we wouldn't want to do that. I'm going to zoom this out. Woo, hello, like that. And I'm going to draw this like this. And I want you to draw this graph right here, because this is the graph that I want to look at, okay? This is the graph that establishes this thing that we call Hooke's law. I think it's because Newton wanted a fourth law, and he wanted this to be his law, and that's why I got so upset at Hooke, but I'm not positive that that's true. This graph right here establishes what we call Hooke's law. It's not a very mind-blowing law, my friends, okay? It just says that as the displacement of a spring gets bigger, or as it stretches more, the spring force gets bigger. It's true. Y equals mx, right? Fs, the spring force, is equal to some constant times the displacement. And that some constant is not just some constant, we call it the spring constant. Whoa, what? And we use the letter, anybody know? Want to guess? K. I don't know why. Seems like it should be S, but it's not. K. K is the spring constant for any spring. So the springs that we used back there were all manufactured to have exactly the same spring constant. So if we went back and did the math to figure out what the slope of this line is, if we have Fs and X here, then you all should get the same value, okay? But that value, that spring constant value, will not be the same as the spring that's in your car that serves as the shocks for your car, right? You guys know that there are springs in your car that serve as the shock. So when you go over like a speed bump, you don't just bounce and bounce and bounce and bounce and bounce and bounce forever, right? Okay, but it also goes to go doo-doo, which would be super uncomfortable, right? So that's why there are those springs. Question for you. Which do you think has a bigger spring constant? The spring in your car or the spring that you just used over there? Think about it. And make sure that you're not just given a 50-50 shot, but that you have a reason to think about it. What would the graph of something that was like your car look like? Would it be a steeper line or would it be a shallower line? Josh, you look like you think you have an answer. You share it with us?
Yeah, I said that the car spring would have a higher constant because it generally has to move a lot more mass than what this would.
Okay.
And I don't really know how far it stretches, but I'm sure it's not like that far. So X,
Not like, yeah.
X would never really be that big, but it still has to give a lot of force.
Sure. Yeah, so it's going to be a really steep, yes. So the stiffer the spring, the higher the spring constant. A slinky has a really, really low spring constant, right? Okay, because it just goes, wah. Yeah. Okay. One little thing that we didn't add here is that the spring in Hooke's law, we're back to directionality, and that matters. Hooke's law says that the spring force will always try to restore the spring to its original size, okay, to its original equilibrium. So the force will always pull back in a direction that's opposite the displacement. So if you stretch the spring force is going to be pulling back in. If you squish the spring force is going to be pushing out. So the direction of the displacement and the direction of the force are always opposite one another, okay? The statement of Hooke's law says that the force of a spring is always proportional to its displacement from equilibrium and always in the direction opposite of the displacement. I will tell you that College Board loves this definition, this two-part definition, okay? They love the fact that not only is it always proportional to the displacement, but it's also always in a direction opposite of the displacement, okay? They love it. I see it a lot on problems, so I want to make sure that you know that you see that and you understand it, okay? But at this point, you're probably saying, Ms. Carveling, we are done with free body diagrams. We haven't done those forever. We are in the chapter or the unit on what? Energy and on work. So what are we doing here? And I'm going to tell you, you've seen this stuff before. You have a force acting over a distance. A force acting over a distance does what? It does work. It changes the amount of energy in a system. I don't know if y'all saw it, but Brady just did this. What? Yeah, I mean, it's true, right? This is a big, big deal. So we've got a force acting over a distance, and that gives us work. Now, friends, we have said for a bunch of times, and I need your attention. I know that we're getting close, but we're not quite there yet. Work is equal to, it is equal to change in energy. It's also equal to a force acting over a distance. Usually, like when we're lifting something up to give an object some gravitational potential energy, it's a constant force. But is this a constant force today? Is it a constant force over that distance? Well, look at the force. Does the force stay constant? Friends, if the force was constant, the graph would look like this. Well, I mean, this is a straight line, but if the force was constant, it would look like this, wouldn't it? Is the force constant? No, it's not. You have a changing force. Changing force over a distance. We got to figure out how to find the work. Yeah? Yeah. It's not a big scary area. It's just a triangle. Okay? The work done to change the energy. And friends, what kind of energy do you think this might be? What'd you say? It's a kind of potential energy, but it's not gravitational potential energy now because we're storing energy in the spring. This is spring potential energy, U sub S. Okay? Right? Is equal to, all right, friends, you know how to find the area of a triangle, don't you? Yeah, it's 1/2. What? Base times height. So here we go. So we're going to do 1/2. The base is the displacement, X, and the height is the force, the spring force, right? Okay. Now, that's all cute and well and good, but that's really not where we want to leave it. So we're going to do one more step. Here we go. Hey, wait. Fs is equal to Kx. Oh, that's cute. So really, instead of saying Fs, we can just say Kx. So let's do it. Here it comes. So we've got U sub S. The stored energy within a spring is equal to 1/2. Oh, well, it's X times Kx. That negative was just to tell us direction. And we don't care about direction when we're talking about energy. So we got 1/2 X times Kx. That's a lot of X's to write down. Instead, we can write it as 1/2 Kx squared. That's something worthy of putting a box around. Okay? Hey, real quick, will you check the units of this thing? What should the units of this thing be? That's a good question. Well, it's an energy, so it should be what? It should be in joules. So you need to prove to me that this is equal to this is in joules. You're like, but what's K in? Well, that's a really good question, but you can figure it out. Let's do it. Here we go. We're just going to do this fast. Force is measured in newtons. X is measured in meters or centimeters. We're going to do meters. The units of K then have got to be newtons per meter. Are you with me there? I guess. Sure. I mean, it's got to be, right? In order to make this thing work, it's got to be. So the units of, excuse me, the spring constant are newtons per meter. So you got newtons per meter times meters squared, which gives you what? Newton times meter, and a newton meter is a? Oh. So this is in joules. How are we doing, team? We doing okay? Bell's going to ring in just a moment or two. I have got a sheet that I want you to work on. It's got some energy in it. It's got some springs in it. It's even got some energy bar charts in it. It's got so much stuff. I know you can't wait. So come up and get one to make sure that your day is complete. I don't want to disappoint.